What I'd like to talk to you now is about the development of oil in the Arctic Ocean, primarily by British Petroleum. And North Star was one of the first of the islands that British Petroleum created in order to drill for oil in the Arctic Ocean. You might notice that this has some interesting features. It's got some really large equipment on it. It has a very large retaining wall, and you'll see the purpose of the retaining wall here in just a second. So what we're looking at here is the north slope of Alaska. In the center, we have Prudhoe Bay, which was the first large oil discovery up in this region. Kuparuk is the oil development off to the west. And North Star is the first of the offshore drilling platforms that were constructed. It's not the only one. If you look a little bit to the east of Prudhoe Bay, there's one called Endicott. And Endicott is actually one that I visited to kind of learn more about the process by which they create these islands and the work that goes into actually extracting oil from the continental shelf up in the Arctic Ocean. So North Star is located 6 miles off the coast, and they construct this island, and then they run a pipeline at the bottom of the ocean, and then they bring that onshore, and then they pump it another 11 miles to get to pumping station number 1, which is the first entry point for the Trans-Alaska Pipeline, which will eventually pump the oil all the way to the port of Valdez. The island itself was constructed in 39 feet of water, 6 miles offshore. It cost more than $700 million to construct, and it was initiated in 2001 and started operation in 2002. So, as I mentioned before, one of the things they have to construct these islands to withstand is the offshore ice. So here's a picture of the ice pack. It moves with the wind, it moves with the ocean currents, and it's pretty much an immovable force, and that's why they have these huge retaining walls to prevent the ice from riding up on top of the island and destroying all of the equipment there. It's also really cold there during winter. Here's an example of wind chill conditions between -45 and -60 degrees Fahrenheit. And in order to construct these islands, they actually doing it during the winter. And one of the reasons they do that is that they can construct ice roads on top of the sea ice by spreading out liquid water and having it freeze. And they build up a rather substantial layer of ice that they can then drive heavy equipment on without fear that it'll fall through. So here's an example during the construction of the North Star. We have an ice road that is leading out to this area. The dump trucks have done their job, and they have completely created an artificial island off the coast. And there'll be additional work that'll be going on with putting in the retaining walls and laying the pipes and bringing in the equipment to place on the island, because it needs to be fabricated elsewhere and then transported. So here's an image of the work in progress to actually lay the pipeline from North Star to the shore. And there are several different steps in the process, but they bring out the pipes and then they weld them in place, check the welds, and then drop them into the bottom of the ocean all in one step. And here we have a little diagram that'll show that here on the next one. So once again, we have the trench, the diggers, which are cutting the hole in the ice. We have the welding machine off to the right, and then we have several kind of tracked cranes, which then take the welded pipe and push it to the bottom of the ocean, which is only about 40 feet deep. So here is North Star after the retaining wall has started to be constructed. And they've got cranes and whatnot trying to finish the construction of the island itself. And then once they get the island constructed, then they have to bring in the equipment. And here's an example of the type of equipment which needs to be transported to the island. So this was actually constructed in the Los Angeles area, and then it was put on a barge and taken all the way to Alaska through the Bering Strait and then up into the Arctic Ocean. And of course, this can only happen during summer when the area happens to be ice-free. So here's an example of the equipment on a barge. And so here is the island itself with the pumping equipment on it, the drill rig on the right, and all of the other things that are necessary to make this a functioning drill pad and well pad. It started operation in early 2002, and its peak production from this particular facility was about 68,000 barrels per day. Which is quite impressive. So how do they get that oil to market? Well, the way they do that is through the Trans-Alaska Pipeline, or TAPS. And the TAPS was constructed in the early 1970s to bring the Prudhoe Bay oil to market. It cost several $billions. It was completely privately funded by a consortium of oil companies. And they had to use a variety of different construction techniques depending upon whether or not they were constructing the pipeline on permafrost, on kind of seasonal permafrost, or on areas that don't have permafrost. And just to remind you, permafrost is land, or essentially soil, that remains permanently frozen below zero. So the pipeline stretches all the way from Prudhoe Bay all the way down to the port of Valdez on the Gulf of Alaska. And it has to cross 3 mountain ranges. It has to cross the Brooks Range, the Alaska Range, and the Chugach Mountains. It has several different pumping stations. These pumping stations serve a couple of purposes. One, they monitor the flow. They give it enough energy to move uphill so that it can cross these ranges. And they also can be remotely controlled to stop the flow of oil if a leak is detected anywhere along the 800 miles of the pipeline itself. The oil comes out of the ground at about 170 degrees Fahrenheit because it's from deep in the earth, and it gets warm as you move deeper and deeper. And by the time, so they put in at Prudhoe Bay at 170 degrees, and by the time they get down to Valdez, the oil has cooled off to about 85 degrees Fahrenheit. So the different construction zones that they had to deal with were the cold permafrost on the north slope, which is primarily completely frozen year-round. Then they have the warm permafrost, where you have an active layer on the top that is melting during the summer. And then the last southern portion in the Chugach Mountains, there's no permafrost at all. So what exactly is permafrost? Well, it's that soil that remains at temperatures below freezing. And there's an active layer on the top, which basically melts during the summertime when the temperature rises above 32 degrees Fahrenheit. And then, in other parts of the year, it freezes solid again. The construction is such that they try and put the posts for the Trans-Alaska Pipeline deep into the permanent permafrost so that it can remain steady and solid. So here we have an example. We have the pipeline, which is 4 feet in diameter, made out of 1-inch steel. And then that is sitting on one of these cross beams. And those cross beams have 2 supports which go deep into the permafrost and right through the active layer. But remember that the oil is warm, and so it warms up the pipeline and it warms up the superstructure that's holding it up. And the cross members actually have heat exchangers. That's what those tall things are on top of the post, to try and liberate that heat back to the atmosphere so that it doesn't go into the ground and melt the permafrost. So they also put the pipeline in a zigzag configuration for 2 reasons. 1, to deal with seismic events, to give it a little bit of wiggle room, and 2, as the temperature changes outside, the length of the pipeline itself changes due to the expansion or contraction of the metal itself. And so they have to have some ability for the pipeline to change its overall length. They do have periodic anchors which lock it in place, and then it's allowed to free float over much of the other areas. So here's an example of one of the anchors. The pipeline is locked in place at this point, and then you have the radiators, the heat exchangers on top, trying to prevent it from melting, the permafrost underneath. So under typical conditions, the support beams stay frozen inside the permafrost, but over time, if the heat exchangers aren't working perfectly, or if climate happen to be changing, or you have a particularly warm conditions, you can actually thaw the area underneath the pipeline, and that can cause the supports to start to become unstable. And here's an example of a support that has started to become unstable, and the pipeline has shifted because of that. And so in order to do that, they have to go back and put in a new support, put it deeper so that it can actually make it to the permanent permafrost. And they do maintenance, routine maintenance on the pipeline each year. It requires maintenance. There was also a lot of infrastructure that went in. So here's an example of a bridge for the pipeline. It's a dedicated bridge for the pipeline to get it over this particular river. But this is not the most impressive bridge structure for the pipeline. That was actually over the Yukon River on the next slide. So here we have a suspension bridge that is bringing the pipeline over the Yukon River, which is the largest river in Alaska. And you can imagine if there was a leak here that would be a pretty significant problem right into the river. The oil companies also constructed this permanent bridge over the Yukon River, which happens to be the only bridge across the Yukon River in Alaska, and it's the beginning of the Haul Road, which is the 600 or 700 mile road from Fairbanks, Alaska, all the way up to Prudhoe Bay. It's used primarily by trucks for deliveries. So here we have the output of the Trans-Alaska Pipeline. So finished construction in the mid to late 1970s. Production quickly ramped up to 1.5 million barrels a day, and by the late 1980s, it was up to 2 million barrels a day, which was the limit for the pipeline. And then it started to gradually decrease as the rate of production from the various reservoirs started to decrease. The oil companies weren't happy about the reduction in the flow-through the pipeline, so they were continuing to do exploration. And that's in the early 2000s is when they got the idea to build the offshore islands to tap into reservoirs underneath the continental shelf, and they were able to boost production again and keep it rather steady between 700 and 900,000 barrels a day. So the port of Valdez in the Gulf of Alaska is a sheltered port that has a normal way that the tankers move in and out from the port, but you might recognize in this figure that there's a Bly Reef just to the east of the main tanker lines, and that is the infamous location of the Exxon Valdez tanker that ran into the reef when it strayed from the intended course, causing, at that time, one of the world's largest oil spills into Prince William Sound. And all of these nooks and crannies and all of these inlets were coated in significant amount of oil, caused untold damage to wildlife and the ecosystem. And to this day, you can still go to these beaches and dig down and find oil remnants. Even though they spent billions of dollars trying to clean it up, it's still there. So here's a picture of a tanker that is leaving the port of Valdez. It's a beautiful location. And where does that oil go? Well, some of that oil goes to the west coast of the U.S. There are refineries north of Seattle, and there are refineries in the Los Angeles region. Some of that oil goes there, some of it goes to Hawaii, and some of it actually goes to Asia. So here is an example of a pumping station. So this one is in direct communication with the headquarters in Anchorage, where they monitor the performance of the pumping station and the flow rates, and they can basically shut off the flow of oil with a push of a button at any point should any issues arise. So one of the other things I want to highlight is the construction of drill pads and the ability of the Arctic tundra to recover over time. So because the area up on the North Slope is permafrost, they can't build the oil wells and the drilling stuff right on top of the surface because it will melt and will cause the structures to become unstable. So one of the strategies that they've done is to dredge gravel from the riverbeds and then deposit it on top of the tundra to create a stable base for the drilling operations. And they can basically use that drill pad to drill the wells and then for operations. And then once the operations are done, they're required by law to remove all of the equipment and help the area become revegetated. And so here we have an example of a drill pad about 8 to 10 feet tall of gravel. And this is 5 years after the drill pad and all of the infrastructure was removed. And you can see that the vegetation is starting to return. And here is a picture 10 years later. So this is 15 years from the location of the 15 years from the removal of the equipment, and the vegetation is starting to fill in. And here is 25 years after the removal of the well pad and equipment and infrastructure, and you can see that it's pretty well revegetated, but it's different. It's obviously been impacted by the activities, and it's not going to look exactly like the surroundings, in part because of all the gravel. They also needed to build roads to construct the drill pads, and in the 1970s, this is the type of road that they would create. It did a lot of damage to the tundra, and it was quite messy, sort of thing. And so this is immediately after they were done using the road, and they started trying to revegetate it. After 5 years, we'll see what it looks like in the next slide. So after 5 years, not much vegetation has actually taken root here. We'll look at it after another 10 years. So this will be 15 years after the retirement of the road. So 15 years, you can clearly see the location of the road. It is vegetated, but the vegetation is different than the surrounding vegetation. And now we have one that's 25 years after. So 25 years after, the vegetation is still different. You can still see where the road was at, and this has done a lot of long-term damage to the environment. So the oil companies realized that their roads were causing a lot of damage, so they developed a new strategy, and their new strategy was to do the construction of all of the drill pads during the winter time. And the reason they do it during the winter time is that they can use water to essentially create ice roads. And so they can build up a thick layer of ice across the tundra, and they can drive their heavy trucks across that. And then in the spring and summer, when the ice road melts, the tundra underneath is undamaged and unblemished from their activities. So there is one other thing that's in the works that you should be aware of. And Prudhoe Bay, the Trans-Alaska Pipeline was only intended to last about 30 years. And it's now about 45 years old, so it requires a lot of maintenance in order to be able to keep it operational. But as long as they're continuing to pump oil, it's worth it for the maintenance. However, once the oil fields are played out up there on the North Slope, the oil companies will have to spend millions, if not billions of dollars to remove all the equipment from northern Alaska and recycle it. And so one of the things they want to do is they would like to figure out a way to bring their natural gas to market. So recall that the oil reservoir also has a lot of gas in it, but because they had no way to bring that gas to market, they've just been re-injecting that natural gas back down into the wells. It helps keep the pressure up in the wells, and it stores this resource for long term. And what they would like to do is do a privately funded gas pipeline, a natural gas pipeline, to connect to the pipeline that extends up into Alberta and then extends all the way down into Chicago. So the blue line here is an already existing natural gas pipeline, and the pink and the green are suggested alternatives for where they could actually build the pipeline. The pink one is the northern route, and that primarily goes through Canada. And the green one basically follows the Trans-Alaska Pipeline down to Fairbanks and then takes a turn to the east to make it across the Yukon and British Columbia to hook up in Alberta. So this pipeline is really important for the future of the North Slope oil operations because it would allow them to continue to pump oil at a lower rate while they are trying to bring their natural gas reserves to market. And they anticipate that they would probably have anywhere from 30 to 50 to 60 years worth of natural gas that they could transport from the North Slope to the lower 48 if they were allowed to build this pipeline. They would also, of course, if they're going to be continuing operations in the North Slope, they would also like to find additional sources of oil so that they can keep the Trans-Alaska Pipeline operating simultaneously. And the largest known oil reserve up there is in the Arctic National Wildlife Refuge. And so that is going to be the topic of discussion and debate in our next class. And I want to give you a background on the Arctic National Wildlife Refuge and the oil reserves so that you can have a better basic understanding of the most important issues associated with drilling in this sensitive region. So there are other issues to consider. So when you want to decide whether or not you want to drill, you have to look at the effects of the exploration on the tundra and the effects of the production on the wildlife. You have potential environmental spills, and we have a lot of costly infrastructure that's already in place. And the Native Americans, most of them actually want the development, and 80% of Alaskans want the development. So these are arguments in favor of continuing operations on the North Slope and expanding them into the Arctic National Wildlife Refuge and expanding them into the export of natural gas.